Thank you. So this is a little outline of what I'm going to be doing. What I would like to do is talk a little bit about the state of the art, where we are now. I can really only kind of touch on that because there's a lot of stuff going on, and it's changing every day, obviously, as well. Then I want to talk a little bit about some of the work that needs to be done for future progress in artificial intelligence, and then some of the broader implications. So one of the things that I'll try and emphasize in this talk is the wider applications of ideas in computer science. It's not just a new technology that will, make certain things easier or less expensive to do, but this really has roots and connections with a wide variety of other intellectual topics. But first, to talk a little bit about the state of the art, I want to go back to some early predictions about AI. AI is usually dated from roughly 1950. This is a quote from Alan Turing, who was one of the main founders of the whole discipline of computer science. And many of you know about the work he did on code breaking during World War II. And he said in 1950 in an article on machine intelligence, the use of words in general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. So that's actually kind of a modest prediction, 50 years in the advance. Here's some less modest predictions. Herb Simon, you may know, got a Nobel Prize in economics. Newell and Simon were early researchers in AI. So already in 1958, they declared there are now in the world machines that think, that learn, and that create. And they predicted that within 10 years, there would be a machine would be the world chess champion, would prove an important new mathematical theorem, and compose critically acclaimed music. Well, none of those things happened. In fact, arguably, none of them have happened yet. Well, the chess, maybe, perhaps. Another prediction here from Simon is that machines will be capable within 20 years, so he's talking about 1985, of doing any work that a man can do. Now these quotes all happen to be from Newell and Simon, but this was a common opinion among AI researchers. They thought that they had basically sort of the secret sauce that was going to allow us to put intelligence inside of a computer, and that within a very short period of time, because computers are faster than our brains, we would have machines that were as intelligent and doing everything that humans could do, but better. So that hasn't happened. So it's interesting to understand why that hasn't happened and why some of these factors may have changed. Nevertheless, there was some very interesting progress. So one key event was Arthur Samuel, working at IBM, developed a machine that would play checkers, a program, I should say, that would play checkers, and it would improve its performance. And so it was a learning program. And he got the clever idea because actually it pretty quickly got better than he was able to play checkers. And so in a sense, he couldn't teach it anymore. But he said, well, I can put this program playing against itself. And since IBM wanted to burn in its computers, have them run for diagnostics and things like that before they shipped them to customers, he said, well, just let my program run on your computers that would otherwise be idle. And so the program got better and better and better, and by 1959 it defeated one of the best US checker players. So one of the important points about this, aside from being an early example of machine learning, is it disproves the idea that the machine can do only what its programmer knew how to do. Yes, Arthur Samuel knew how to play checkers, but not how to play it very well. The machine was able to go beyond what he was able to tell it how to do. So when we think about what machines may be able to do, it's important to keep in mind that they're not necessarily, yes, we have to understand the learning mechanisms that we put into the machine, but once it's got that learning mechanism, then it can learn things that we don't know. So I'm skipping over a lot of the history of artificial intelligence here, but I want to give you several key aspects of it. So much of the AI that led to those overly optimistic predictions is now known as good old-fashioned AI, or sometimes symbolic AI. And the idea is that it was based on a model of knowledge that says that basically when we understand things at some level in our brain, that information is represented like sentences, propositions, things that are true or false. And that thinking then was a process of reasoning. So this is something that mathematicians and logicians had studied really for centuries, but especially was highly developed in the 19th century and the 20th century. And people had started to study how to mechanize this formal, logical, inferential process. And since the AI researchers, like many cognitive scientists and psychologists at the time, believed this was the essence of thinking, they said, well, computers can do this. They can do it much faster than people. Therefore, they ought to be able to do this. So it used logic-like knowledge representation, propositions. It took the view that cognitive processes are some kind of reasoning, even if we're not aware of the reasoning, that at some level our brains were doing this. It was kind of at perhaps a subconscious level. So this didn't work. The first failure was they found that some of their very general reasoning programs could work on kind of toy problems, but they couldn't really deal with big problems. And they realized the problem was they didn't know anything. They could reason, but they didn't know anything. So they said, okay, it's not enough to have this reasoning engine. We also have to have a lot of knowledge. And this led to a new phase in AI in the 1970s and 80s, mostly in the 70s, that was called expert systems. The idea was you could go, catch an expert, get them to tell you how they were thinking through a problem, encode this all into, again, sentence-like rules, often if-then statements, and put that into the computer, and it could then would have the expertise of a human being. So the point here is this is really rooted in a deep intellectualist tradition in European philosophy going back into the Enlightenment. The idea that the essence of the human mind was our reasoning ability and our linguistic abilities. The other things we do are not so important because animals do them, quote unquote, non-human animals. So for example, walking, talking, feeding ourselves, running around, catching balls, all of these sorts of things that animals also do quite well, that's not really distinctly human stuff. So the focus was on things that were considered distinctly human. But this led to what's been called a cognitive inversion in AI, that early AI systems could do things like learn to play checkers at an expert level, do quite well in chess, solve logical problems, prove some mathematical theorems that are hard for most human beings, but other things that are very easy for human beings, like just walking around or feeding yourself, they couldn't do at all. So things that were easy for humans were hard for the AI systems, and vice versa. And the reason was because it was the model of what thinking was, or what cognition was based on these very high-level activities of reasoning. So ultimately, these approaches failed. And in the late 1970s and early 1980s, more and more people were recognizing that these approaches were they would get up to a certain point, sort of an advanced beginner level, and then they would be stuck. They would never get to that expert level. So people started looking around and saying, okay, obviously we've got some things wrong here. What's wrong? And it's really kind of a basic insight. It says, okay, humans can do these things. Therefore, brains do these things. Maybe we should try and figure out how brains do these things. And so this led to a new approach in artificial intelligence beginning in the 1980s it's usually called artificial neural networks, or connectionism is another name for it, the new AI, which basically said, we're not going to try and model these very high-level abstract processes. We're going to try and look at what's going on in the interconnections between the neurons and how neurons interact with each other, because that's how our brains work, and then based on that design systems. So this is an example of artificial intelligence systems inspired by the brain. And a lot of the success you read about now in AI systems in the news is based on these artificial neural network approaches. The other thing I want to mention is that this is not, again, purely a technological advancement. For many years, philosophers and psychologists have been criticizing good old-fashioned AI, saying, look, we gave up on those ideas long ago. We know that stuff doesn't work. And in particular, philosophers studying phenomenology and phenomenological psychology had some important insights into the way we actually acquire knowledge and understand the world and behave in it. And so a lot of this connectionist work was inspired from these insights from phenomenological philosophy and psychology. This is kind of predominantly an Anglo-American approach to cognition, and this is more of a continental approach to cognition. And so a lot of the foundational work came from that angle. The key thing is that information is not represented in terms of these sort of language-like structures, namely at the symbolic level. It's represented in terms of these many microscopic interconnections between little sub-symbolic facts or bits of information. Whereas in the old AI, people thought that regardless of how you learn something, ultimately it would be encoded in something somewhat like a verbal definition, like you would look up in a dictionary. Here, it was understood that concepts arise and are learned through experience and might never be encoded in some sort of definition-like structure. They could be encoded just in thousands or millions of very low-level interconnections between little bits of information. So this then has been the new approach to AI since really beginning in the mid-1980s, but it's really only in the last decade, with the accessibility of vast amounts of data and vast amounts of computing power, that it's really shown its superiority. So this is an example of the AlphaGo Zero program, learning how to play Go, which of course is an extremely complicated game, arguably much more complicated than chess, over the course of 40 days, from not even knowing the rules of the game to learning how to play the game correctly, up to the point where it was performing at a level better than the best human experts. Again, showing that the people that program the system don't have to know how to do whatever it is themselves. The system can learn itself. These, you've read about deep fakes probably. So this is an example where this person's face was essentially pasted in here. But this is not just like a Photoshop pasting of one image onto another, because the neural network is understanding the structure, how the surface appearance of this person relates to movements of the person. And then that information is being run backwards, in effect, with a different face. So this is why this deep fake technology can allow you to, say, deliver a speech and put President Obama's face on it, and it will look like President Obama delivering it as opposed to somebody else. So this technology is getting better and better all the time, and of course it raises some serious problems in terms of telling whether a video or any other signal source, it could also be an audio signal, is correct or is manufactured in this sort of way. One of the ways this works, again, it goes back to Samuel's checkers program. We use adversarial networks where one network is trying to generate the fake, the other network is trying to detect it's a fake, and they're both getting better over time. So it's essentially, we engineer an arms race between these different technologies so this technology gets better. And this software is available for free on the web. People can go out and just use it. So that's you know, a disturbing capability. Now here's some recent robots. These are from Boston Dynamics. This is called Atlas. This is called Spot. There's lots of really wonderful videos on YouTube. I'll just show you this short one of Atlas. So the point is that now we're getting much better at doing these low-level things. Now this is something, well, you know, most people could do some approximation of this, but these were things that robots couldn't do at all a few years ago. You know, if you had a robot with maybe 3 wheels on it, it would very slowly creep along and try and find its way. So this is because they're using biologically inspired techniques for both controlling the robot, and then of course you can see it has, in this case, kind of a humanoid kind of shape as well. This video is from just a few months ago. So we've a lot of progress here in terms of giving robots physical competence. And again, it's the sort of physical competence that many people have and many animals have, but was very difficult to do. So lots of other stuff. Let me go back here. I mentioned also language translation I didn't mention. Google Translate is getting better and better every year, again, because it's got more data to go on. So these are just a few classical AI applications that have really improved in recent years, and are largely through the use of these connectionist approaches. Okay, so what's the bad news? So I want to point out some of the gaps between these AI systems and, in particular, natural intelligence, human and non-human animal intelligence, and see where we might be able to do a little bit better with these. So one of them is classification errors. One of the things we get computers do is classify things. Now this could be classifying, is this a loan application we should approve or a loan application we shouldn't approve? Is it a mortgage we should allow or a mortgage we shouldn't? Should we hire this person? Should we not hire this person? Your driverless cars, looking at things ahead of it on the road and deciding what it has to do about them. So here's an example, a typical neural network thing. This neural network has been programmed, I should say trained, it's not programmed, it's trained to recognize a bunch of objects, a bunch of everyday objects. So you give it an example of an image of the object and you tell it what it is, and you give it thousands of these and enough computer time and it will learn to do it. So here you can see, if you can, it's a little hard to read, but it had very high probability that this is a banana, a very small probability that it was a slug, but yeah, you can kind of see why it might think it's a little bit like a slug, and then no probability that it's a snail, an orange, and 100 other things, okay? So that's fine, that's considered a successful neural network. Now what they've done is they've crafted this funny little abstract looking little thing here, and if you put this near the banana, now it says, oh, it's a toaster. And in fact, there's virtually very little probability that it thinks it's a banana, okay? Now, so of course that's kind of disturbing, because that's not a small error, okay? That's a major error, and in particular, it's a totally incomprehensible error, okay? There's all sorts of things you might imagine it would mistake this for, but a toaster is not one of them. So, you know, this is a problem. And there have been examples done with this with driverless cars, where you got a stop sign and you put a little sticker like this on a stop sign and it says, oh, it's a 45-mile-per-hour sign. Okay? So we need to understand why this happens. And there's been a lot of work done on it, and we do to some extent understand why it happens. But one of the points here is the sort of error this is making is a very unnatural error. It's not the sort of error we make. We make mistakes too, right? We misperceive things. But we don't make mistakes like this. So this shows that this AI system is operating in a very different way than our perceptual systems. And we need to understand that better and hopefully make the AI system so it works, so it has more robust behavior. This is not robust behavior. Small, irrelevant change, and it's completely wrong classification. Okay, and we want robust perceptual behavior, especially if something very important depends on it, like what the obstacle is ahead of you in the road. Okay, here's another thing that AI people do, has many practical applications. You take an image in the AI system, recognizes various objects and their relationships in the image, and then tries to summarize them in a sentence or a phrase. So it's captioning the picture. So here's a picture, and here's the caption generated by the AI system. A woman riding a horse on a dirt road. Well, I don't know if it's a woman or a man, but you know, it's a reasonably accurate statement, right? But it misses the whole point. Okay, it misses the significant part of the image. And partly that's because AI systems have a different sense of relevance than what we do. Here's another example. Care to guess what the caption is this time? An airplane is parked on the tarmac at an airport. You know, and you can, there's the airplane. It's kind of parked, I guess. That's something that, because it's near an airplane, you might assume is tarmac. You know, it's, you know, okay. So, so it's interesting to understand why it makes these kinds of errors. Okay, so if you have an AI system that you want to sort through millions of images and try and pick out ones that are important for some purpose, this is not going to do it. And here's the last example. Oh, and there's the, I'll let you look at it first, and then there's the caption. Okay, so this is partly what's showing you that this is not just sort of a disinterested interpretive activity. That there's some notion of relevance and what is of interest and important to human beings that these systems are not doing. So these systems don't automatically have a human-oriented sense of relevance. And that's something then, for many purposes, we want our systems to have. So we have to think about, well, how do we give it that? You know, we come with a sense of relevance. Food is relevant to us, right? Because we have to eat. Sleep is relevant to us, and so on. But an AI system doesn't have any sort of built-in sense of relevance, so we have to train it or give it to it in some other way. These are all learning systems, but they take vast amounts of data. That's why there's been success over the last 10 years, is that we have just enormous computing power. We can have servers with just thousands of processors. And we have gigabytes worth of data we can suck off the internet and use to train these neural networks. But that's, again, not the way animals learn. We can learn from a small number of examples, very limited data. Often even with just a single case. I can show you a picture of an animal you've never seen before, tell you what it is, and you'll remember it. Okay, maybe not perfectly, but you'll basically remember it. So many animals exhibit single case learning. You burn your finger once, you remember that. Transfer learning is another one. Because these systems are based on experience that's just acquired from doing whatever it is over and over again, it's difficult. These systems don't tend to extract general rules from what they're doing that then can be used to train another system or to train the system on new types of tasks. So the sorts of things, again, that the old AI did better, this new AI does not do so well. And reinforcement learning, which is what we use for teaching the programs to play games, for example, where we basically, it does a bunch of actions and they either succeed or they fail, and based on that success or failure, that modifies then what they do in the future. Despite enormous successes like on the AlphaGo Zero, this is still quite different from the way people learn. For example, if a person learns to play one video game and gets good at it, they can transfer much of that knowledge to a different video game. They can just learn what's different about the rules or the way the game operates and still transfer a lot of their expertise. Whereas with most of the reinforcement systems we've got so far, they would essentially have to start over from zero again on a new game. So we need to understand learning better. This, of course, is the sort of thing that psychologists study and also neuroscientists. Explanation. So people are using neural networks now for many different purposes. I mentioned loans and mortgages and hiring decisions, national security decisions, all sorts of things. And again, your car, your driverless car, deciding whether to stop or not. Especially when it makes a mistake, you would like to know why, right? And so if a person even makes a gut decision, they can usually give some post hoc rationalization of it. And that has some meaning. And you know, if you ask the person, well, you know, why did you offer the woman 80% of what you offered the man? They might say, well, you know, this reason or that reason, I think women should be paid less. You say, well, no, I'm sorry, that's bad reasoning, you know, and it's also illegal. Don't do it, you know, and that then will modify the behavior of the system. So we like explanations of things, especially when they don't work, so that we can correct them. And these neural network-based systems, because there are no rules that they're following, it's very difficult to have them give some verbalizable reason for what they're doing. They just do it because they've been trained that that's the answers they should give. So this is important for many of the applications of neural networks now, because these neural networks can essentially, because they're learning from experience, if the past is biased, they will just kind of learn that's the way things are, and those biases then will be incorporated into their future behavior. And so we have to go out of our way so that they don't get trained in this biased kind of way. The last gap I want to talk about has to do with sensory-motor behavior. Now, I showed you a nice example there, the Atlas robot from Boston Dynamics, and many of their other robots are very good also. But I have to say, those are videos produced by Boston Dynamics, kind of showing, you know, the best examples of this. So this is still that cognitive inversion, that things that we do very well are quite difficult for computers, and it's important to understand why. So this was a DARPA project, a grand challenge for which they awarded a lot of money, millions of dollars, to have different companies produce robots that were able to do simple stuff. Walk around, climb a set of stairs, turn a valve, you know, things you might want to send a robot into some sort of disaster after an earthquake or something like that, and just have it do some useful stuff. So this was 2015, so it's a couple of years ago, but pretty recent. And again, these are, well, there we go. These are some of the best systems from industry and research, or industry and universities at the time. Okay, and again, they're not just, you know, a little bit uncoordinated or a little bit slow. They are not able to do very basic stuff. I like this one. Again, supposedly trying to open a door, okay? Okay, now, you know, we sometimes stumble and fall too, but not quite so systematically. Now watch this one. Oh no, not the one. You see, you've got to try and turn that knob, or that valve rather. Now watch. Grasps where the valve isn't, turns it, and then falls over. Okay, so again, this is the cognitive inversion. This is simple stuff, right? If a person can't do this, they probably got some sort of disability. Animals can do many of these things too. And here we have state-of-the-art, as of a couple of years ago, AI systems that are not able to do it. And this makes the Boston Dynamics stuff even more remarkable. Now here's something else, another example in the same sensory motor area. So a few years ago, a research team announced that they had got a robot to fold a towel, and that was a really big deal. And the press kind of laughed at them, like, okay, folding a towel, that's really sophisticated, right? Well, it is hard, because if you try and do these things mathematically, fabrics are complicated. They don't have just a few joints. They don't have simple shapes. They fold, you know. They've got a lot of complicated properties. And so, but again, we handle it quite well because we don't try and think these things through like a mathematical equation. So here you can see, and I want to point out, this is running at 3 times speed. It's been sped up by a factor of 3, okay? And it's this strange kabuki process that it's doing here. And if you watch this, it's telling you all of the different stages of this process, which certainly is not part of our process when we do this, right? This is laying it on a table. Spreading the garment. This is the next big task it has to do. And this is the way it's working out what it has to do. That's right. Yeah, and this is, again, 3 times speed. But look at all of the kind of strange motions it's doing. Now, again, you know, you could fold something like this in the dark, right? You could fold it in it might not be the best folding job, but you could fold it in the dark without seeing anything, without all of this processing. So these robots, even these relatively newer ones, are doing these things in a very different way than we do them. And this is an example not of sensorimotor competence, but sensorimotor incompetence. Even though it finally manages to get the job done, it does it in such an awkward way that it's not very effective.
Is it so slow because it's running through billions of computations?
Exactly. That's exactly what it's doing. And it's doing these very sophisticated things about it. Has an idea of what the shape of the shirt is, and if the actual image of the shirt doesn't fit its shape, then it has to, you know, and we see this early shaking process is to just shake it out so it's kind of extended so it knows where its parts are. And I'm sure they found that now we're going at 10 times speed. And it's still painfully slow to watch.
Does it handle static cling?
Probably not very well. So you see, all of these things are very idealized. And, you know, they're relatively small objects that they're folding. They're all apparently a similar kind of, probably cotton kind of material. All of these things affect it, okay? So I like to contrast that with this. Okay, so it's something that we've all seen dogs do, other animals do equally amazing things, but it's not amazing, right? It's an everyday sort of thing. A dog runs, jumps, catches a frisbee in the air, okay? With neurons that run at very slow speeds, 1,000,000 times slower than our computer. And this body is not as simple as those robot arms, or even something like Atlas. And so it's coordinating this very complicated body, you know, which doesn't have simple joints and simple sensors to nevertheless do this very complicated task. So this is what we want to understand better, is how a dog or any other animal manages to do this complex sensorimotor coordination. So again, whereas the early AI researchers were looking at the top of the intellectual pyramid, if you like, activities like proving symbolic logic theorems, playing chess, solving complicated logical puzzles. And, you know, they weren't so concerned about stuff that we do, you know, as well, or sometimes not as well as other animals, like walking, okay, running. They thought, well, that's the most important stuff, because that's the distinctly human part of our minds, was this higher intellectual stuff. What we understand better now is that they got the picture wrong, that you need all of those lower level things, that sensorimotor coordination, the fact that your intelligence is embodied in a physical body interacting with a physical world. That's the foundation on which all of those higher level cognitive activities are based. And you can't just sort of cut them off and say we don't care about that. You actually have to have all of that stuff to have the higher level things work better. And so that's why it's so important to get robots that can actually walk and find their way around in the world, because that's the foundation then for the much more complicated activities that we would also like to have them do. So again, the trouble with soft, flexible, irregularly shaped things is that they're too complicated to analyze mathematically. They have too many joints, if you want to look at them that way. Too many degrees of freedom is another way we put it. But nevertheless, they're not a problem for us. And probably for a trained chimpanzee, you know. In applying robots in car manufacturing, you know, it's really, well, comparatively easy to get the robot to do welding and stuff like that. But one of the really hard problems is to get it to put up the fabric lining inside the car, because again, it's flexible. You'd think flexible stuff would be easier to deal with than heavy, rigid stuff, but not necessarily. So, so those are some of the gaps. Now getting into some ones a little bit further from what you might expect. As I mentioned, the old AI was based on an ideal of pure rationality. They said emotions, that's what gets us into trouble. So if we can have AI systems that are just these logical engines, they will be much more intelligent than human beings are. And over the past century or less, really, we've begun to realize the fallacy in that in fact emotional intelligence is very important, obviously in social situations, but even in individual decision making. So how does this apply to AI? One reason is it's useful to have AI systems be able to understand human emotions. So there's been a lot of work on this, looking at people's faces and inferring what their emotional state is, and their body language as well. So if you take an example, like if you've got a robot astronaut that's cooperating with human astronauts to, say, build a space station, it's a cooperative activity. And if you think of a cooperative activity like moving a big couch through a doorway with another person, you know, you're doing a lot of reading of their body language to negotiate exactly how you do that. And so the robot has to have that same sensitivity of understanding what we're trying to do and being able to understand whether you're getting frustrated, whether you're in pain, whether you're afraid, you know, what's going on in you so that it can cooperate in an effective way. So it's important for AI systems to be able to read human emotions. But they're kind of just understanding them intellectually, you know? It's kind of like the way you try and figure out what whether your dog's happy or sad. You know, it's a lot of it it's an inferential process. That raises the question about, especially in these cooperative contexts, well, shouldn't the AI system also be able to express emotions? You know, because that's part of the communicative process, is we're each expressing something about our internal state, and we need to understand that. And again, there's been quite a bit of research on this, on getting AI systems to express different kinds of emotions. Here's some recent humanoid robots that are pretty good at their emotional expressions. I'll show you another little video here while I talk about this. So, so they're just showing some of the different emotions this system can display. This one has control of all of the sort of micro muscles that we're not even conscious of in our face, but we subconsciously are aware of them, so that you know, that tells you when somebody's smiling but they're really unhappy. We can still detect that in many cases because of the micromuscular behavior. So this is getting pretty good at doing that. So here's an interesting question, I think. If we have AI systems, robots perhaps, that are very good at expressing emotions, but they don't feel emotions, what do we think about that? Now, if you have a person who intellectually can realize what emotion they should be expressing and can do it very realistically, but they don't feel that emotion, we usually call those people psychopaths, right? They're using their emotional expression in a manipulative way. And so, you know, if an AI system is expressing emotions that it doesn't actually feel, you know, it's a little bit, it's at very least manipulative. And so I think it's interesting to think about that. But that then raises the question, okay, and I'll just go back here. It's important that they be able to express emotions, but we're a little bit, we should be a little bit concerned about fake emotions. The other case where this occurs, and this is a very active area of application now, is robot caregivers and robot companions. So if you want to use robots for child care, or you want to use robots for elder care, you know, sometimes they look like cuddly little pets and stuff like that, and they act like they're happy to see you and all of these sorts of things, but of course they're not happy or anything else in that sense. So, you know, is there something wrong with that, or is that okay to have these systems that are not feeling anything, acting like they like you or dislike you or want your attention or something like that, want to play with you? And so this is you know, seen as one, you know, very important possible application area for future robots, because, you know, there's just a large demand for them. And then so one thing that might lead you to say is, okay, maybe the robots should feel emotions. You know, there's nothing that says a robot shouldn't feel an emotion, and in fact, arguably, they should. Emotions have enormous survival value. All of the higher order organisms, more complex organisms, have emotions. It's an important survival tool. And probably, if we understood it well enough, and we do understand some of it, we would see that it's also important for robots. And in fact, there's good evidence for that. That in fact, for effective decision making, you need a functional emotional system. And so I'm just going to mention here some work by Antonio Damasio that he wrote about in his book, Descartes' Error. And he talked about a patient that he called Elliot. And this person had damage to both of his prefrontal cortices, and in particular in a region that, as I'll show in a moment, represents various emotional states and values. After that damage, Elliot lost his feelings, his ability to experience the emotions. He knew what they were. He could define them. He could describe how they used to feel. In other words, he had a complete intellectual understanding of emotions, you know, comparable to what any of us would have, but he couldn't feel them anymore. So he became a Mr. Spock, if you like, okay? Rational agent, but with no emotional capacity. The interesting thing is he couldn't make rational decisions anymore. He could do all of the analysis, all the pros and cons, all of that sort of stuff, but when it came to making a choice, he couldn't do it. That's where we kind of consult our gut, we might say, and say, okay, you know, what is the overall weight of the evidence here, and what do I want to do? And I won't go through all of the detail here, but basically, as information, this is the back of the brain here, as information moves forward in the brain, in this what pathway, the brain tends to figure out what it's looking at in this case, because it's vision. In this other how pathway, it tends to figure out what to do about it. And you can see here that the representations go from more concrete to more abstract. But more important, now this is a front view, this is where our eyeball is here. You can see here on the outside of our surfaces of our brains, there's this sort of cold rational processing, but on the inside medial surfaces between the hemispheres is where the hot processing takes place. This is where we evaluate various sorts of emotional and evaluative activities. And this is a map of some of them. These are things where we weigh various sorts of values, avoidance, aversion, what's the cost of an action as opposed to what are the anticipated rewards of an action, emotionally considered, okay? How good is it going to make me feel versus how hard or painful might it be to do it? And so all of these things are being represented here in various areas in the medial frontal cortex of our brains. And that was destroyed in the case of the patient Elliot. And this stuff then affects how we perceive things. Okay? Perception is not just a pipeline where stuff comes in our eyeballs and then gets further and further processed until we make a decision. It's a very much of an interactive process from higher level processes down to the sensory periphery and back and forth. So these values in particular then actually condition what stands out to us, what we notice. This came out just last week in Nature Communications. what they did was they ran some movies and mapped the various areas of the brain that were active. And this is at this temporal parietal junction. So this is further back on the sides of the brain. And you can see here different patterns of activity for happiness, surprise, fear, sadness, anger, disgust, and then some more abstract parameters of polarity. That's whether it's good or bad, basically, or attractive or unattractive, complexity and intensity. And they were able to analyze these activities. So this stuff that goes on in our brain, there's no reason in principle we can't build something like this into a computer if we understand it well enough, so that we could build a computer that has emotional representations and can view things from not purely a perceptual or a rational perspective, but also a affective or emotional aspect. Okay, so what do we need to get there? Well, I'm not going to say a huge amount about this, but I'm going to talk about two primary areas of research: neuroscience and neurocomputing. So we've been most successful with these brain-inspired approaches to artificial intelligence. Again, we're taking a system that works pretty well, trying to reverse engineer it and understand why it works, how it works. But there are still enormous unsolved problems in neuroscience. Part of the problem is that the nervous system is spread over, depending on how you count them, 6 or 7 orders of magnitude of size, from 1 meter scale things in the central nervous system down to 1 angstrom scale things, the individual molecules that represent neurotransmitters and other parts of the nervous system. And so you can't always just study one of these levels in isolation. That often interacts with multiple levels, and that just makes it very hard to do. So we need to understand more general principles of neural representation. How are things represented in the brain? So that we can design artificial systems that have similar ways of representing information. Episodic memory. You remember where you parked your car? Probably. I don't always, but probably. You remember what you had for dinner last night? This is episodic memory. You didn't try to remember it, probably. Maybe you tried to remember where your car is. You probably didn't try to remember what you had for dinner. Okay, but you remember it anyway for a little while. Okay, this is a single occurrence memory. One exposure, you remember it. And you remember all sorts of things about yesterday and this morning just automatically. So we don't understand very well how that works. We understand it better in the case of the brain, but our AI systems don't do this very well. Attention is another important one. Even with things like playing games, part of what separates the experts from the beginners is they know what to focus in on. They ignore a lot of extraneous stuff. It's not like they consider it and say, oh, that's not important, oh, that's not important, oh, that's not important. Because there's too many things that are unimportant. But they can kind of zoom in on what is most important, devote all of their cognitive energy to analyzing that, and then make a good decision. Executive control, that stuff our prefrontal cortex does of planning higher order activities, planning your college career, right? Planning your after college career, deciding what to take next semester, or deciding, how to work on a particular project or assignment. These are all instances of executive control where we're dealing with higher level organization, and also with these values, right? What's important, what's not important, what's going to be hard, what's going to be uncomfortable, and so forth, putting all of those things together. Language. A lot of progress on language, but like the translation stuff, it's still very much at the surface syntactic level. When you go to Google Translate, it may do a decent job of translating, but it doesn't understand a word of what it translated, okay? We need to understand better how it is we understand language and then use that. And interestingly enough, abstract reasoning, the stuff that the old AI was pretty good at, the new AI is not so good at because it works from the bottom up. So we're kind of working our way up through, lobster level intelligence and rat level intelligence and monkey level intelligence, and hopefully getting to human level intelligence with enough research. So So we need lots of, these are the things that some of the things that neuroscientists are working on, and those of us in the AI field are basically piggybacking on them, taking what they've done, trying to understand it in more abstract terms, independent of the nervous system, so we can apply it in our artificial systems. And then we need better hardware. What we do now is we run these AI programs, like I said, on vast server farms that fill warehouses, generate vast amounts of pollutants. Well, not necessarily pollutants, but heat certainly. Use a lot of electricity, and still run much slower than the brain. The trick is that the brain is massively parallel. There's about 13 million neurons per square centimeter of cortex. And if you take your brain out and flatten out the cortex, it's about the size of 4 sheets of 8.5 by 11 paper. So every one of those square centimeters has about 13 million neurons in it. And then there are subcortical areas of the brain that have even more neurons in it. So lots and lots of neurons, even though they operate at millisecond time scales, which is about 1 million times slower than our chips now. Okay? So it makes up for very slow speed by very large numbers of neurons that may be connected to 10,000 or in some cases a couple 100,000 other neurons. So very densely interconnected. So we've got about 86 billion neurons in our brain, and something like 1,000 times that number of connections in our brain. So the basic idea of connectionism is the information, the knowledge is stored in the connections. So we have lots of connections to store that information. So we need to be able to do the large-scale wiring of the brain, connecting together all of these different areas with simulated or artificial neurons if we want to achieve a similar kind of computation. Because even a rat, you know, its cortex is about the size of a postage stamp. But that's already something like 20 million neurons, okay, in that little rat brain. So, and that's why rats can do some amazing stuff. They've got a lot of neurons. So we need new computer hardware as well that's based more on the way the brain works. Okay, I'd like to take the last few minutes here talking about some implications of this. So this was Richard Feynman, the Nobel-winning physicist, Blackboard, when he died. He was at Caltech. What it says up here is, what I cannot create, I do not understand. This was one of his philosophies. If you really know, if you really understand something, you ought to be able to make it. Okay, and that's really the fundamental goal I see of artificial intelligence. If we really understand intelligence, we ought to be able to make something that's intelligent, other than the usual way. Make it out of different stuff, for example, in a different way. This has implications for all sorts of areas in philosophy. We've seen universals or concepts. How are they learned? How are they acquired? How are they used? Well, AI can help us to understand that, to test different theories. Epistemology, what is knowledge and how is knowledge acquired? Language, what's the relationship of the mind and the body? We've seen it's actually much more closely related than 18th century and 19th century philosophers thought. In fact, arguably, the mind can only emerge from the body. Perennial problems like free will. Okay, we can make a robot. Say we make a robot that's intelligent as a human being, you know, and acts to all respects like a human being. Will have free will? Well, you know, you may say yes, you may say no, but unless you can explain why this machine that's made out of, say, silicon doesn't have free will, whereas we do, if that would be your statement, you really don't understand it. You have to be able to explain what is it about us and the machine that is either the same or the different with respect to free will. And consciousness, again, also. If you had a machine that had the sort of cognitive behavior of a human being, would it be conscious? Well, you know, we've all got opinions about it, but we can't give an in-principle answer of what it is about our brains that makes us conscious, okay? But if we had another system that was in some respects very similar to us and in other respects quite different from us, that would give us another way to talk about that problem. So having the potential, at least, of an AI allows us to address many of these long-standing philosophical puzzles in a new way. Okay, suppose we did have a robot that had the cognitive capacities of a human being. Would it have rights? Well, this is kind of a science fiction idea, because we're far away from this. You know, I don't think we're going to have a robot with human capabilities in general for, you know, a decade at least. But nevertheless, this guy, David Gunkel, this arrived in my mailbox actually yesterday, and he asked, how do we think about this previously unthinkable question? Or, excuse me, how we think about this previously unthinkable question will have lasting consequences for us, for others, and for our moral and legal systems. Again, the issue is not so much whether you say yes or no. The issue is why. What does it mean to have a right? This applies also to animal rights. What does it mean to have a right? What does a right do? What does it mean? How do you acquire rights? And so thinking about robot rights allows us to address some of these issues, as it mentioned here, our ethical responsibility to robots, perhaps, and also from robots. And legal personhood. There's already a European Commission resolution on civil laws of civil law rules of robotics. And again, practical situations, if robots are used as war fighters and they do something against the laws of war, like killing a civilian, well, who's accountable? Is the robot accountable? Well, that seems kind of silly to most people, but you know, if it's truly an autonomous robot, maybe that would make sense. But in any sense, we have to think about what is the locus of legal responsibility and ethical responsibility for actions. Because again, we've got robots that are doing things they weren't programmed to do. They learned to do them from their experiences. And then finally, I know I'm out of time, so let me just pose this question. There's a question of superhuman intelligence. If we can make an artificial brain with our brains have 86 billion neurons, and they operate at a sub 1 kilohertz frequency, less than 1,000 impulses per second. Our artificial systems will probably not be made out of neurons. They'll be made out of some sort of chips or something. Our current chips operate 1,000,000 times faster than our neurons. If we can make a system with 86 billion neurons, we could probably make one with 200 billion neurons, right? It's just a little bit bigger. So what happens if you make a system with many more neurons than we've got in our brain? Of course, this presumes we already know how to connect them, so that's some of the other stuff I showed you. And they're operating 1,000,000 times faster. That would be a superhuman intelligence. And I don't see any reason in principle why this won't happen. Okay? We could argue about how long it will take, I think, but I don't see any reason why we won't eventually know enough to be able to do this. So these are some intentionally provocative remarks from some computer scientists. Hans Moravec at Carnegie Mellon wrote this book, Mind Children, in 1988. He said, we humans will benefit for a time from their labors, but sooner or later, like natural children, they will seek their own fortunes while we, their aged parents, silently fade away. Well, this is sort of the optimistic view, actually. This is a computer scientist, AI researcher at MIT, Ed Fredkin, says, it is fairly difficult to imagine how you can have a machine that's millions of times smarter than the smartest person, and yet is really our slave, doing what we want. They may condescend to talk to us, they may play games that we like to play, and in some sense, they might keep us as pets. Again, a lot of people consider these ideas a little bit silly, but you have to try, if it's silly, you have to kind of find out where the silliness arises, where is the gap in the reasoning or the projection and obviously then the ethical, social, political issues of if we can do this, okay, should we do it? Well, these guys, or at least Moravec, is saying, yeah, this is the natural next stage in human evolution. And for us to complain about it is kind of like Neanderthals sitting around saying, well, I don't know about these Homo sapiens. They're kind of smart, but I don't like them so much, and they're replacing us, you know. So And he said, you know, that we would now consider that sort of a short-sighted attitude, or maybe a parochial attitude. And he says we should view this the same way. We're creating our mind children that will succeed us evolutionarily. Obviously, a lot of people don't like that idea, you know. But again, so then the why is the important thing. So this then is my last slide. This is again from Herb Simon. I disagree with a lot of things about him, but he does say some smart stuff too. Perhaps the greatest significance of the computer lies in its impact on man's view of himself. The computer aids him to obey for the first time the ancient injunction, know thyself. Because the computer, the AI system, gives us potentially a different sort of sentient, intelligent thing on this earth that's different from us in many respects. It allows us to really understand ourselves better. We got that other that we can use to reflect ourselves against and compare ourselves with. So I'm sorry for going too long here, but that's where I'll stop.